It's the cold, dark winter of Louisiana, so y'all get used to it. Listen, guys, we don't have. After today we have break next week. I don't know if y'all are aware of that, but we will have class again on Thursday. We are what? What? Okay. It's like having a heckler or something out in the crowd. We'll have class on Thursday, and we need to have the second part of Chapter 2 reading quiz soon. Let's do it on Thursday. No, I'm joking. We'll do it on the next. We'll do it on Tuesday, guys. So if finish up that chapter, we'll probably finish it up today, and then we'll have a reading quiz on the Tuesday after we get back. Okay, so not the immediate Thursday. We'll come back here on that Thursday, and then the next time we'll have chapter 2 reading quiz. In that time, we'll go on to chapter 3. So, and then we'll have a reading quiz soon after that for chapter 3. But the next exam's not coming up for like a whole month. So we have a whole month coming up. That exam will likely include 2, 3, and 4. So, yeah. Or maybe just 2 and 3. We'll see. We miss a week, so it's not really that long. Y'all have any questions? Our big plans for the break? You're going to study the whole break? Sleep? You're going to... Okay, thank you for your on. Elise, what? Oh, good. Yeah. You don't look like you're pregnant with twins. Oh, I know, I was joking. That was a joke. Ha ha ha. She said her godchild's being born. Are you? All right. We're going to Hattiesburg, if anybody cares. Does anybody care? We usually get out of town because we live like right on the parade route, or like a block off parade route, and it gets a little crazy around our house, so we just go out of town. So if we live on 6th Street, so if anybody wants to go party at our house, then you can. On East 6th? Yeah, we live on the east side. Huh? That's fine. Just watch out for our big dog, because he'll get you. All right. Left off with plus 12, the Poiseuille, okay. Poiseuille. Yeah, the Poiseuille equation. And a couple other different things like the flow equation. We had the flow equation which said this A1V1 equals A2V2. This will come up again soon. With these equations, guys, I'm not looking so much for calculations, but on the exam coming up in a few weeks, a month or so, I'll be looking for relationships. So for example, if I have a pipe that gets smaller like this, what happens to the velocity in this part of the pipe? Does it A, increase, B, decrease, or C, stay the same? A, increase, B, decrease, or C, stay the same? The velocity in this part of the pipe, what happens to it according to the flow equation? I think I asked the same question last time, but just to jog your memory. This will come up again today when we talk about the circulatory system. I'm going to go and write the Poiseuille equation. All right, just a few more seconds. I'll stop at 52. 52. Okay, very good. The velocity increases. Remember, did y'all go home and do your garden hose thing? You get your thumb on the end of the garden? You did? Ashley, right? Ashley. And it goes a lot faster. You can squirt your... Okay, yeah. All right, and then, so according to this equation, what happens to the flow rate for more viscous, with an increase, in viscosity? That is, if the viscosity increases, what happens to the flow rate? You can use these same options. Does the flow rate increase? Does the flow rate decrease? Or does it stay the same? All right, I'll stop at 20 at 30 seconds. Okay, excellent. It will decrease. You need to know what all these variables mean, okay? This is my viscosity, and this is my flow rate. If I see an increase in the viscosity, I see a decrease in the flow rate. That makes intuitive sense, right? Like if I make it thicker, it's going to flow at a lower rate. Which of these are the units for viscosity? Tell me. Is it a meter squared second? Is it meters per second? Is it meters cubed per second? Or is it meter seconds cubed? Which of these are the units for the flow rate? That's Q. Which of these are the units for the flow rate? Meter squared seconds, meters per second, meters cubed per second, or meter seconds cubed? Remember what flow rate is. Hey, who went to lunch yesterday and when you were drinking your soft drink or whatever, you told your friend, hey, if this was a superfluid, it would just come out the bottom of the cup? Who said that? Isn't that cool? It's like the container's not in there. It's like if I was a superfluid, I could walk through that wall because there would be no viscosity between me and the wall. All right. Just a few more seconds. I'll stop at 1 minute. Good morning, Macy. See? Hey, that's right. See, it's volume per time, so that's meters cubed per second. Very good. So let's move on now to the applications portion of this chapter in chapter 2. Make sure I started this. Yeah. We're going to first talk about the circulatory system. I'm going to sort of hit the high points. And gosh, there's a lot of information about the heart. And I know that a lot of you probably know all that information, but I want you to have sort of the basics of where the blood flows and some of the things that are relevant. So I'm going to hit those high points here. And you can go back to your book for more details, but really I'm just going to hold you responsible for what we're going over today. Is that clear? Because it gets all the valves, which I'm sure that all of you know, right? Y'all know all the valves in the heart? Yeah, most of you do. I do not. So the circulatory system, there are two parts of the circulatory system. There is the systemic part, or the systemic circuit. Good morning. And then there's also the pulmonary circuit. Which is the longer of the two? Right, the systemic is a lot longer than the pulmonary circuit because the systemic circuit takes blood from your heart, enriched blood from your heart, and takes it throughout your entire body, and then it brings it back to your heart. And then the pulmonary circuit takes it from your heart to where? To your lungs. So this just goes like a couple inches. So it's really short, right, to go from your heart to your lungs, the pulmonary circuit. So number one takes blood to the body. And then the pulmonary circuit takes it from the heart to the lungs. All right. We'll consider this to be a closed system. Because all these things that we're talking about, they don't exactly hold true unless we're talking about a closed system. So the Poiseuille equation and the flow equation and all that business, if you don't have a closed system, then they're not exactly going to hold true. So we're going to consider it to be a closed system, even though we know that the circulatory system isn't exactly a closed system because there's transfers of fluids all throughout that system. But we'll consider it to be a closed system, and that'll be close enough. So the result of being a closed system is that the flow rate is constant. Do you remember the one equation that was based on that principle? Well, which one was that? That was that A1V1 equals A2V2. So this is from I think they called it the flow equation, if I'm not mistaken. Is that what they called it? They called it something else. Yeah, the flow rate equation. That's the premise for the flow rate equation. All right, so we'll assume it to be constant. Now, for a viscous fluid, you need a continual drop in pressure to make it flow. If you have an entirely non-viscous fluid, like the supercooled helium, then you don't need a change in pressure. But for a viscous fluid, which in reality is every fluid, you need a continuous drop in pressure. And that comes out into our Poiseuille equation because we have that delta P term, that pi r to the fourth. Remember that gave the size of the container times delta P over 8 eta L. So this is that continual drop in pressure. We talked about this pressure differential, that the bigger that pressure differential is, the more flow that you're going to have. And whenever you have a viscous fluid, like blood, for example, you need a continual drop in pressure. So within the body, you're going to see a pressure difference all the way throughout the body. Now, in the body, the blood will flow from the aorta coming out of the heart to the arteries. And as I said, the book gives more detail than this, but I just really want you to know this sort of basic path that the blood follows. The arteries, the what? Arterioles, yes. From the arterioles to the capillaries. What happens to the size of these as you go out into the body? They gradually get smaller and smaller and smaller. That'll come back to bite us in just a second, okay? And then after the capillaries, after it's given all the oxygen to the body, then it comes back to the heart through the venules. Am I saying that correctly? Yeah. So y'all know this, right? Okay, good. Through the venules and then back to the veins and then the vena cava. Yeah. The vena cava, which is like the really big thing going back into the heart. The big vein going back into the heart. Okay? So you need to know this basic path. If you don't know it already, you'll see it probably on the test coming up. All right? And the order of those as well. All right? So this is all enriched blood flowing through these, and then this is the deoxygenated blood that's going back to the heart. And then it'll go through the heart back into the pulmonary circuit where it is given fresh oxygen. All right, there are 4 chambers in the heart. And there's a nice picture in your book. I'll show you another picture in just a second. Can I go down from here, folks? All right, there are 4 chambers in the heart. There is the left and right ventricles and the left and right atria. I'll show you a picture in just a second. That is the left atrium and the right atrium. All right. So blood flows. There's a picture in your book here. Flows out of the left ventricle. Sorry, guys. Through the aorta. Sorry, give me just a second, okay? It goes through the systemic circuit. So the left ventricle is pumping that blood through the systemic circuit. Goes to all your legs and your body, all the way throughout your body. And it returns to the right atrium. Right. Once it gets there from the right atrium, it goes to the, do y'all know where? Right ventricle, goodness. Then this is that used blood goes to the right ventricle. Through the pulmonary artery to the lungs. And returns to the left atrium. Through the pulmonary vein. It didn't say this in your book, but it's my understanding, and y'all can correct me if I'm wrong, because I might be, that arteries lead away from the heart and veins lead into the heart, correct? Okay. Okay, I think that's it. Yeah. All right. So you'll need to know those 4 basic chambers and sort of how the blood goes in and out of those chambers and where it goes from those chambers. Let me show you a little picture. There's one in your book. I think I have the same book. Oh, actually, I mean, just note here, you don't need to know the names, but there are 4 one-way valves in the heart. And these are basically just to regulate the flow. They actually prevent the blood from flowing back when the heart is contracting and relaxing, to keep the blood from flowing back. So you have blood that go in one direction but not in the other direction. Let me show you a figure, and then I have a little video I want to show you about the heart. I think this is it. Yeah, here we go. This is actually the picture from your book. So it comes, let's see, where does it come out of? The left ventricle. Left ventricle through the aorta. Am I right about this? I just learned this last night. I don't know if y'all can tell. Can you tell? Yeah, you can tell. So it comes out of the left ventricle through the aorta, and then it goes to all throughout the body, and then it comes back through the what? The vena cava? Is that right? Yeah, it comes back through the vena cava and goes into the right ventricle, which for some reason is on the left side. I don't understand. Do y'all understand? Oh, it's mirrored. Okay. So, and then from the right ventricle, it goes to the pulmonary artery, and then it goes to the lungs, and then it'll come back through the, oh yeah, here it is, pulmonary vein, back into the left ventricle, and then it does the whole thing again. This is a really nice picture. I think it shows you, even shows me, who has no knowledge of this, how this works. All right, I have a little video here. Oh, there are the valves. You don't need to know the names of them, but the aortic valve, the mitral valve, mitral, and there are a couple others which I can't see right now. Thank y'all. I appreciate that. That's okay. All right, I have a little bit. All right, so let's look at some more about the circulatory system. As we said, there is a continual drop in pressure. Where is the pressure greatest? This is the question. Is the pressure greatest in the aorta, in the vena cava, or in the capillaries? Where is the pressure the greatest? Aorta, vena cava, or the capillaries? Very sorry, guys. I don't know what's up here. Where's the pressure greatest? I have a continual drop in pressure from the heart all the way throughout the body until it comes back. So where is that pressure greatest? And again, this continual drop in pressure comes from the Plus-Lee equation, which says that Q is pi r to the fourth delta P over 8 eta L. So I have to have this drop in pressure in order to get up here. All right, I'll stop at 48, about 5 more seconds. Okay, aorta's right. It's starting in the aorta, right? And then it goes through the whole body. So our highest pressure has to be at the beginning point. And then as it goes through the body, it will gradually decrease. We'll see that in a little bit more as it returns back to the heart. All right, so there's this continual drop in pressure. I've already said this, but the systemic circuit is much longer than the pulmonary circuit. So since L is really big, I want to still get that same flow rate. I also have to have a much larger potential change in pressure. So since the systemic circuit is so much longer than the pulmonary circuit, the pressure there should be higher initially. The pressure differential is much higher. Just because it's trying to push this viscous fluid, this blood, through a much longer tube. And I actually talked about this in the video a little bit. Gosh, what is it that pushes the part of the heart that pushes it to the aorta? Which ventricle? Yeah, the left ventricle. And it talks about how that's a really strong part of the heart to give it a higher pressure to push it through the aorta. By the way, which principle is that an application of? When I contract that left ventricle and push the blood through the aorta, what principle is that we've studied so far? Famous physicist guy, theologian, philosopher. Huh? Adam? That's the Pascal's principle. That's what you were going to say. Yeah, Pascal's principle, where if I apply a pressure to a fluid, that pressure is felt all the way throughout the fluid. So when you apply a pressure to the heart, that pressure is felt all the way throughout the fluid. All right, typically these pressures, just to give you an idea of what the pressures are, the systemic circuit, the pressure of the blood in the systemic circuit is something like 80 to 120. This is in millimeters of mercury. And in the pulmonary circuit, it's much lower. Again, it's much lower because L in the Plus-Lee occasion, I feel French every time I say it, is much longer. So in the pulmonary circuit, it is 10 to about 25. You see a big difference in the pressure of the fluids in these, a factor of 5 or so difference between those, or more even. All right? Any questions about the circulatory system? There are more details in your book, and you're welcome to go there. You do need to read the book, but this is really what I'm going to expect you to know. Yeah? Yes. All right. Let's look at the blood pressure measurements. Guys, I just want to remind you, too, over the break, if you're just looking for stuff to do, you can start looking through your book and maybe find a chapter that you want to write your chapter review on, your book review. Yeah, Destiny. Yeah, you can do that. I'll need to know a little bit beforehand so I can plan for it. If you don't want to write and you feel more comfortable speaking in front of a group, then you can do that, too. I expect it to be, informative, and I'll probably ask some questions, and other people ask questions too. Did I give a time on it? Okay, yeah, 5 to 7-ish minutes. All right? On the long side of 5, not the short side of 5. Okay, so blood pressure measurements. First of all, are blood pressure measurements, are they absolute or gauge pressures? Are they absolute or gauge pressure? So back in the early part of this chapter, we talked about when you measure your blood pressure, is that a measure of the absolute pressure, or is that a measure of the gauge pressure? The blood pressure measurements. Like with the cuff, is that an absolute or a gauge measurement? All right, I'll stop at 38, about 5 more seconds. Okay, very good. This is a gauge measurement. A good way of telling that, who put C? Was C an answer? No. You're just trying to be funny, aren't you? Maybe they just misclicked it. Thank you, Casey. Okay, so gauge pressure. A good way of telling if it's a gauge pressure or not is if you have no pressure on it, does it say 0? And like with a blood pressure measurement, it would say 0. But you know that the pressure there is something because you're in the atmosphere. Remember the tire with no air in it? It reads 0, but the pressure isn't really 0. And also, do blood pressure measurements, do they measure the pressure in your systemic circuit? Or do they measure pressure in the pulmonary circuit? When you measure your blood pressure, do they measure in the systemic or the pulmonary? All right, I'll stop at 25. Oh, let's see. What? Trying to think. Y'all get a joke at 100%, right? Yeah, let me think of one. What did the fish say when it ran into the concrete wall? Damn. Huh? What did the fish say when it ran into the concrete wall? Damn. Yeah. I would apologize for cursing, but I wasn't cursing. I was just saying, damn. All right? Okay, good job. Well, first of all, you measure your blood pressure, you typically measure it on your arm, right? And that's part of your systemic circuit. Because your pulmonary circuit, you'd have to stick something into your heart or whatever. I don't know how they measure that, if they measure it at all. Does anybody know how they measure the pulmonary circuit pressure? I don't know. There are more invasive methods of measuring blood pressure. So that's one key, that's your systemic circuit. And then also if you look at your numbers, like we're going to look at 2 numbers. And for example, 2 numbers for good blood pressure is 120 over 80. I'm not asking a question. No. So typically 120 over 80 are good blood pressure measurements. And remember from the previous one, when we talked about the systemic, this 80 to 120, that is our pressure in the systemic system. Now they're different. There's a range there because of reasons that we'll talk about in just a second. Probably reasons that you already know. Okay. So 120, this top number, and I'll just call it 120 from here, is the pressure when what? Right, when the heart contracts. Right, so this is called the systolic pressure. So you need to know just sort of what systolic pressure is if you don't already. Systolic actually means contraction, or well, what else does it mean? It's drawing them together, I think. Yeah, it means contraction. Then the number 80 is the pressure when the heart relaxes. And this is called the diastolic pressure. Right, and the diastolic actually means a drawing apart, diastolic. It means a drawing apart. So again, this is an application of Pascal's principle. That when I have this heart contracting and applying pressure to the fluid, then that pressure is felt all throughout the fluid. And then when it's not contracting, when it's relaxed, then the pressure is less because the heart is relaxed. All right? So let me just write that. When the heart contracts, P goes up, and when it relaxes, P goes down. And that's a direct result of Pascal's principle, or a direct description of Pascal's principle. All right, I have a little figure. This is from your book. I'll take this away for just a second. Give me just a couple more seconds. I think this is it. Yeah, here we go. This is from your book. Oh, can y'all see that in the back okay? Can't make it bigger. Let me try. Sorry, guys, I'm having a little computer issue here. Give me just a second. So let's resolve it. Anyway, I'm sorry. This is, I can't blow it up, but on this side, this is the pressure, and this is over time. And I have the systolic pressure up here. And then over here, I have the diastolic pressure on the bottom, where on this bottom dashed line. And you can see that it varies going from about 120 to about 80. Again, this is in your book. If you can't see it in the back, I apologize. We'll also get a little beat here, and we'll talk about what that is in just a moment. Right, can I take this away? Oh, there it goes. All right. All right. Now, when you're measuring the diastolic pressure, so it's my understanding, and you'll correct me if I'm wrong, that they put a cuff on your arm, right? And then they blow it up, right? And at some point, the pressure that's applied to your arm exceeds the systolic pressure. And what happens then? They're listening to a stethoscope. What happens then? It stops, right? So when the pressure applied by the cuff exceeds the systolic pressure, then the blood flow stops, and they can hear that with the stethoscope. And have y'all done this before? Measure blood pressure? All right, I've never done it. So, and then they start to relieve the pressure, and at some point they begin to hear a beat again. But then you hear like what do you hear? Okay, that's going to be Michael. A little tap, tap, tap. Okay, so what does that do to? Is my question. So you apply the cuff until the pressure of the cuff exceeds the systolic pressure, right? And that cuts off all blood, so the beating stops. And it's at that point that you can determine what is the systolic pressure, right? What is that top number? Because the pressure, it's going to equal the pressure that's given by the cuff. And then you begin to release pressure on the cuff. Until you hear a tap, tap, tap. Is that what you called it? The first beat is the systolic, sound you hear. Okay. All right. So this isn't exactly right. You apply the cuff until the beating stops, and then you begin releasing the pressure a bit until you begin to hear the first beat, and then that's your systolic, because that's the pressure that is equal to the systolic pressure, right? Okay. And then you release the pressure in cuff until you hear the beating, the first beat, and this is the systolic. All right. And then later, as you continue releasing it, you hear another sound. I don't know what that sound is called, but when you hear this sound, that's the diastolic pressure. Okay, the last sound before you don't hear it anymore. All right. So now I want to know, what is that sound caused by? What is the sound called? The one for the diastolic pressure. Okay. Anyway, this occurs with the diastolic pressure, and I want to know what this is, or what causes this. Is it rotation? All right, all right, all right. Viscosity or laminar flow? All right, let's not have a bar fight break out over blood pressure measurements. Yeah. All right, so what causes the second occurrence, sound, or whatever it is? What causes that? Is it the rotation of the blood? Is it turbulence in the blood? The viscosity of blood? Or is it the laminar flow of blood? You understand what I'm asking? Oh, yeah, you understand. Okay. Hey. And take their... That's what I want to do, impress them. So maybe I should. Maybe y'all could teach me. All right, I'll stop at 55. 55. So which of these phenomena causes this thing that occurs when you measure the diastolic pressure? Okay, it is the turbulence. And it's my understanding from what I've been reading is that it's turbulence within the heart. Is that correct? When that valve opens up and it whooshes into the heart, and that's what you're hearing. Is that correct? That's a question. Okay. All right. Let's move on, if that's okay. Uh, Valerie, do you have a question? No. Okay. Okay. So what happens according to the flow equation? What happens to V as the area, to the velocity, as the area decreases? Because you've already told me that as you go from the aorta to the capillaries, that the area decreases, correct? As you move from the aorta, which is really, I think it's a centimeter or so wide, to the capillaries, which are tiny, right? What happens to the velocity? Does the velocity A increase? Does it B decrease? Or does it C, does it remain the same all the way throughout the systemic circuit? What happens to the velocity of the blood? According to the flow, I'm sorry, let me restate this. According to the flow equation, what happens to the velocity as the area decreases? According to the flow equation, what happens to the velocity as the area decreases? I think I might have already asked this question, but let's just ask it again. Not necessarily what happens to the blood, but what happens according to the flow equation. What happens to the velocity? I go from a big area to a little area. So what happens to the velocity? All right, just a few more seconds. I'll stop at 105. Okay, the flow is going to increase in velocity. All right, but that doesn't make sense, right? Because as I'm going from my aorta down to my capillaries, what happens to the flow of the blood in the capillaries? Is it faster or slower than what's in the aorta? It's a lot slower, right? Immensely slow, very, very slow, in fact. But the fact does remain that the aorta, when I'm going from an aorta to a capillary, it would look like this. I don't think that's spelled correctly. Okay, don't worry about it. I don't. You know what I'm talking about, right? Now, what explains this discrepancy? Let me give you some options and see if you know what explains this discrepancy. Because clearly the blood does slow down when it goes into the capillaries. But the flow equation, which should also hold true, says that if you move from a big area to a small area, like the garden hose with your thumb over it, that it's going to speed up. So which of these do you think explains this? Does the viscosity of the blood increase? And by the way, if the viscosity of the blood did increase, the flow would go down, right? But is that the reason? Or is it the very long length of the systemic circuit? I want to know, why does the blood travel slower in the capillary than it does in the aorta? Because according to the flow equation, it shouldn't. It should travel faster. Very long length of the system. And if L goes up, then the flow rate should go down. All right. Is it the overall area of the capillaries? is bigger than the aorta? Or is it D, the blood becomes less dense? Which is similar to A, but different. Okay, I wanted to know the flow equation, as we just said, says that as I go from big area to small area, that the velocity should increase, right? But we know that the blood in the aorta travels much faster than the blood in the capillaries throughout your body. So why is that? Which of these reasons explains why blood actually travels slower here than it does in the aorta? Although my picture might be misleading. All right, so which of these reasons gives the true explanation? Does the viscosity of the blood increase? That would explain it, right? If the viscosity goes up, the flow rate goes down according to the Poiseuille equation. Is it the long length of the system? That would also explain it. If L goes up, then the flow would go down. Is it the overall area of the capillaries bigger than the aorta? According to the flow equation, right, that would be true as well, or the blood becomes less dense. I just couldn't think of a fourth option, so I just threw that in. So it's not D. But the top three are reasonable explanations. But what is the true explanation for that? All right, I'm going to stop at 1:15. Who are all these people answering these questions? There's not 50 of you in here, are there? All right, I think we're picking up another class. All right, but C is the right answer. Right, let me show you a picture. I think there's a picture in your book, actually. So if you look at a plot, this is a plot of sort of the area, for example. This is the aorta, and it travels to the arteries, and then the arterioles, and then the capillaries. The capillaries do have a much smaller cross-sectional area than the aorta. Look, there's a lot more of them. I don't know how many, thousands, millions of capillaries in your body? More, right? There are more capillaries than the one aorta, so that the combined area of all the capillaries is much larger than the little stick your finger in the aorta kind of thing. Okay? All right? Is that clear? That's about the size of the aorta. Okay? All right. Yeah, Destiny? I wanted to know, why does the blood travel slower in the capillaries? Right. Velocity increases. That's like putting your thumb on the end of the garden hose. You're decreasing the area, so you increase the flow rate. I asked, why is that true? Why does blood travel slower in the capillaries? And it's because the area of the capillaries is larger than the area of the aorta, because there's so many of them. The velocity does decrease. Yes. So in the capillary, the velocity decreases a lot, like the blood just crawls along, basically. Okay. I'm sorry if I confused you. All right. I don't think so. Oh, yeah, for that first question I did, because the flow equation says that if our area decreases, our velocity increases. But the area doesn't decrease with the capillaries. The area actually increases with the capillaries, because there's so many of them, right? And so they have an overall area that's bigger than the aorta. Is that clear? That's kind of cool, I think. All right. All right, so if you want to deliver medicine to a person through a needle in their arm, Do you insert it into a vein or an artery? And then this will lead into our next one. So I want to do medicine into a person. Do I put it in a vein or do I put it into an artery? I want to put medicine into a person through a needle. I'm going to put a needle in their arm. Do I stick that needle into their vein or do I stick it into an artery? And then think about why, and we'll talk about it. Would I put it into a vein or an artery? You want to think pressure here and why you might want to put in one or the other. All right, stop at 30, just a few more, or 32, a few more seconds. Okay, why would you want to put it into a vein? Huh? Oh, is it closer to the surface? Oh, okay, I didn't know that. Uh, your book says, actually, and I learned this, that the pressure in the artery is bigger or smaller than that in the vein? It's bigger. So you stick a hole in your artery, it's going to start squirting out. So you want to put it in the vein because it has quite a bit lower pressure, right? Because it's further away from the heart, and so it's seen a decrease in pressure. And I guess they're closer to the surface too. Right, but you put it into a vein. That's why it's called an IV, right? Intra what? Intravenous for vein. So when you put it into, when you want to deliver medicine, you put it into a vein because we have lower pressure. I have a little figure here. There's a similar one, I believe, in your book. This just shows the pressure as you go further from the heart. There we go. As we go further from the heart, again, we see the systolic and the diastolic pressure here. But as you go further through the arterioles and the capillaries and the venules and the veins, you get a very low pressure when you actually return back to the heart. So you constantly have this pressure differential as you go from here to high pressures out to lower pressures. And that causes the flow of blood all throughout your body. All right, I'll take this away. Now, guys, I did say that that you didn't need to know all those valves and stuff about the heart, but you do need to go back and read the second part of that chapter for all that stuff because, you know, the reading quizzes is just sort of, have you read the chapter? So you can see some stuff that I haven't covered. I'm just saying you don't need to know the valves, so it seems most of you know them, and some of the minutiae of the parts of the heart. Am I clear on what I'm saying in that? Yeah, so read the chapter, because the reading quiz covers the whole chapter. All right. And the reading quiz will be when? Tuesday, after we come back. Yeah, so not Thursday when we come back, but the following Tuesday. And that'll cover the second part of chapter 2. And then pretty soon thereafter, we'll probably have the first part of chapter 3, or maybe all of chapter 3. Okay. So we have this problem. And if you've ever given an IV, which many of you have, is that true? Some of you have, huh? Nursing. Not your field, right. So if you've given an IV, there's a pretty simple problem as to, you know, how high do I put the bag? You ever had that problem? You don't have to work it out and figure out how high? Okay. All right. So let's just work through this simple problem. I don't want you to worry too much about the math, but I just want you to see how these things are applied in order to determine something like the height of the bag. And then we'll look at some of the dependence on some of the variables. So let's say that I have a bag, I have an IV bag with volume equal to 500 cubic centimeters. All right, cubic centimeters is the same as cc's, which, by the way, is what measure of volume as well. A cubic centimeter is equal to a cc is equal to what? Y'all know what a cc is equal to in volume measurement? A milliliter, right. So a cc is equal to a milliliter. It goes back to how we define what a kilogram is, actually. All right, so I have this 500 cubic centimeter, and let's say that it empties through this IV empties a 20 gauge needle. That has a diameter of about 0.6 millimeters. I think there is a similar problem in your book. They might even use the same numbers. I'm not sure. Is that true, Jessica? Or they use the same numbers in this problem? Were you looking at this problem? They use the exact same numbers? Yeah, okay. So it empties through a 20 gauge needle. The diameter is 0.6 millimeters, and it's a length of about 2 inches. All right. We want this to empty in 30 minutes. So I have this IV bag, and I want it to empty in about 30 minutes. And I want to know how high the bag must be hung. All right, so if I want to know that, a couple things I'll need to calculate. First of all, I want to calculate what must the flow rate be. So remember, flow rate is my volume over time. My volume over time. And so I have a volume of 500 cubic centimeters. And I have a time of 30 minutes. Okay. I could convert that into seconds. Just multiply it times 60 seconds per minute. And that would give me a flow rate of 0.278 milliliters per second, or 0.278 cubic centimeters per second. So the first thing is just what do I want my flow rate to be? Guys, this is in your book if you want. And as I said, don't worry too much about the numbers. I'm not going to ask you to calculate this, but you need to know how it's dependent upon all the variables. But first thing, I just want to find the flow rate. Okay, and so this is the flow rate that I want to get. That's how quickly it needs to come out of the needle and into the person. All right. Then I want to find the pressure differential. So remember from the Poisson equation, Q was equal to, gosh, what is it? Pi r to the fourth, I think. Yeah, pi r to the fourth delta P over 8 eta L. All right. So now I want to calculate what must be my pressure differential, and then I'll be able to figure out what must be the pressure difference between the IV and the pressure in the vein, which we'll take some assumption for that. So let's use this to calculate delta P. And delta P is going to be Q 8 eta L over pi r to the fourth. Again, don't fret the algebra there. I want to show you how it's dependent upon these things. I already have my Q. That's 0.278 cubic centimeters per second. 8 is just a constant. Eta is our viscosity. And the viscosity is given in your book as 0.001. That's measured in Pascal seconds. Pascals times seconds. And then we divide it by pi r to the fourth. This r would be the radius of the needle. I'm not going to write it here because I gave diameter. Radius of needle. And then I can find my change in pressure. And that comes out to be, you have to do a few unit conversions along the way, which I'm not going to require you to do. But you find out that that change in pressure, the pressure differential rather, has to be 4,400 pascals. Remember, what was the atmospheric pressure? Just to give you some reference. It was 1 times 10 to the fifth, 100,000 pascals. So that needs to be the pressure difference between the liquid that is coming into the IV just before it enters your arm and the pressure inside the vein. And that pressure differential will get you that bag out empty in about 30 minutes. So now we can find the pressure differential, or we can find the height, rather. If you recall, back early in this chapter, we said that the pressure due to a liquid is equal to rho times G times H. If I have a certain depth below a fluid, then my pressure is given by this rho GH. Y'all recall this? Yeah, remember we talked about how we walk around with this column of liquid sitting on top of us? And the pressure that does it is that rho GH that pushes down on us and causes atmospheric pressure. Well, a similar thing, if I have a bag, it's a certain height from the bag to where it's in my arm or wherever it is. And so that's the height that we want to know. What is the height between where the bag is and where it goes into your vein? And that's the height that we have here. So I know what my pressure should be, and so it becomes pretty simple just to calculate that pressure. P over rho G. I'll put a base on the P. And I have 4,400 pascals divided by the density of, let's say it's water that you're putting in, or basically water. It has a density of 1,000 kilograms per cubic meter. And the acceleration due to gravity, 10 meters per second squared. And that gives us our height, which is 0.72 meters. So in order to empty this bag in 30 minutes, you'd have to have it be about 75 centimeters, 3/4 of a meter from your from where it's inserted in. All right, that's pretty cool. I know that if you're in the medical field, that you probably don't go through this calculation every time, but it's useful to know this. That's how we determine the flow rate. What happens if this is a blood transfusion? So if we have a blood transfusion, do we need it for a blood transfusion? To get the bag emptied in the same amount of time, do I need to increase H? Or do I need to decrease H? From 0.72 meters. So everything else the same, except now I'm using blood instead of water. What do I need to do? Increase H or decrease H? All right, I'll stop at 42. 42. Okay. We do need to increase H. Let me show you why. What's going to change for blood? In all these equations, which variable is the viscosity is going to change? So if we look over here, our viscosity of blood is bigger. Right? Blood has a greater viscosity. And so that means that I'm going to require a greater change in pressure. And the only way to get a greater change in pressure here is to have a bigger height. So if I have a greater viscosity in this case, like with blood, then I would have to raise it up to a higher level in order to get it to drain in the same amount of time. Right? So really looking on these questions, I want to know how are the variables related to one another. And so if I change one thing, how does it change the other? You're not going to have this calculation by any means on the test, okay? But I do want you to know how these things are related to one another. Yeah? Good? All right. All right, let's look at, so what's another, if you want to empty an IV bag into a person's arm, what's something else that you can do? You can squeeze it, right. So who said that? Kayla? Yeah. So you can squeeze it, and that'll make it go more quickly into the person's arm. What application is that of? Which principle that we've been talking about? Is it, what is it? It's Pascal's principle, just like the heart, right? When the heart pumps, it causes an increase in pressure. And if I squeeze the bag, it causes this to go up, which causes it to go more quickly into your arm, that pressure. All right. Just a few more topics. We're probably not going to finish this chapter today. We'll finish it on Thursday. But It just sort of goes through different parts of the body in the latter parts of this chapter with very short sections, just a few things. The first thing is coronary arteries. You can get arteries that are blocked with cholesterol. And a decrease in the radius because this is what we have here. We have our artery, and then you get this blockage stuff that builds up on the side of the wall, which causes the radius of that artery to decrease at a particular point. And a decrease in the radius then will require you to will require a change in pressure. To keep the same flow rate. All right, so this is my equation. Q is pi r to the fourth delta P divided by 8 eta L. So I'm looking at a decrease in the radius. And so how does that affect the pressure? What must happen to the pressure? It has to go up, right? So the pressure will increase in order to keep this constant flow rate. Remember, this flow rate is, our heart is pumping, right? And it pumps a certain amount of fluid per time. And that flow rate has to remain constant all throughout the body. And if I decrease the radius somewhere along the way, then that pressure has to increase in order to keep that flow rate. Now, this isn't the pressure here. We'll come back to this in just a minute. The pressure here actually does something different. This is the overall pressure of the system has to increase in order to keep this flow rate. All right? That's called, gosh, what is it? Is it called hypertension? Yeah, hypertension, high blood pressure. All right? Actually, something else happens. What happens to the velocity within the blockage? Like at this point, what happens to the velocity of the blood? Does it go up or down? It goes up. Right, so the velocity in here actually increases. And the pressure actually decreases. So here at this point, we're not going to get into Bernoulli's equation. It's not in your book. But Bernoulli's equation says that when you have an increase in velocity, that you actually have a decrease in pressure. So a good example of this is an air wing. So on an airplane wing, roughly looks like this. I have streams of air that come across it. Two streams of air, I imagine them here. One of them breaks and goes this longer path, and then the other just goes straight under. Right? Now my net result is I want to produce lift, right? So I want to have a net force in this direction. That means that I will have a high pressure here and a low pressure here. All right? So which of these streams, the one on the top or the one on the bottom, is going to have a higher velocity? On the top, right. Is this making a lick of sense to y'all? No, let me explain it a little again. I'm trying to show you that when the velocity increases, the pressure actually decreases. So here within this artery, we actually get a decrease in pressure. Are y'all aware of this? But the overall systemic pressure increases, right? But at this location, at this particular location, you get a low pressure. In fact, you can get such a low pressure that the whole artery will just collapse, and then nothing will pass. So when I have high velocity fluids, I get a low pressure. This is just sort of an aside, okay? So you don't need to write this down. But imagine an airplane wing. This is an airplane wing. I have air coming over here. It goes over the wing. And then I also have air that comes along here, goes under the wing. In order to get lift, I have to have a high pressure on the bottom and a low pressure on the top. That gives me lift. High pressure on the bottom, low pressure on the top. The high velocity part is going to be up here in the low pressure because the air has to get from here all the way over to here in the same amount of time that the air gets from here to here. So I get low pressure but high velocity at the top. So when the speed increases of a fluid, you actually get low pressure. That's called Bernoulli's principle. We're not going to see that. That was an aside. Okay? All right, y'all hang on. We just have another minute or so. Also, I want you to notice that a small change in R results in a very large change in P. In the pressure. So just a very small blockage can result in a very large pressure difference. And the reason is because of this. That fourth power, that R to the fourth, if I have a very small change in R, it's going to result in a very large change in P because that R is multiplied by itself 4 times, and that causes a bigger impact on P. Okay, I think we're going to pick up on the lungs next time. I think that's a good place to stop.